This tutorial is exercise 7, and it's the MMC Internal feature. To start off, open up the exercise 7 MMC Internal PDF file. So what we're going to do in this tutorial is we're going to apply the maximum material condition to an internal feature, and we're going to calculate the virtual condition as well as the resultant condition. Now if we look at our flowchart here, the virtual condition, we're using an internal feature which is a hole at maximum material condition, and it's going to be a constant value, and in this case it's going to be our inner boundary. With the resulting condition, again we're using an internal hole, maximum material condition, it's going to be a variable value, and it's going to be the outer boundary of our part and the GD&T. Now again we have our part, so we have a part that has a hole in it, and the hole diameter is 25.1 to 25.5, maximum material condition with a tolerance of 0.1. So we have our two formulas here for the virtual condition as well as the resultant condition, and what I have at the bottom here is an internal feature MMC, and we're going to fill out the chart, and we're going to calculate our virtual, resultant, as well as our tolerances. Now what I'm going to do is we're going to kind of go through steps here, how to fill out this chart. And doing a chart like this is important as you create your GD&T and tolerance. So with both of these I'm doing a hole and a shaft, so you know, a very basic thing is to think of if you have a hole and a shaft, they have to, when you assemble it, meet together. Are they going to be have any interference? Are they going to be able to go in together? So doing, creating your GD&T, creating a chart like this shows you that, what's your virtual condition, what's the inner, what's the outer boundary, are the two components going to fit together. Okay, so we'll go through steps and complete this together. So the first thing I want to do is fill out the feature size. So it starts at 25.5 and it goes down to 25.1. So we're going to go in 0.1 increments down, so it'll be 25.50, 25.40, 25.30, 25.20, and 25.10. Okay, so now we have all the feature sizes, and what we want to do is put in the condition. So in this case we're doing the maximum material condition. So we want to define which I guess feature size has the MMC condition. And in a feature size, when you have a hole, or sorry, like a feature with a hole, the maximum material condition is at the smallest feature size. So our maximum material condition will be at 25.10. Now if we look at the virtual condition, the virtual condition is the maximum material condition feature size minus the feature tolerance. So our tolerance is 0.1, so it'll be 0.10, and that's going to give us our virtual condition of 25.0. Now the virtual condition is constant, and you can see that in our flow chart, that's one of the things about the virtual condition compared to resultant, is the virtual is constant, resultant varies. So as it's constant, every single feature size, no matter what every single feature size has the same virtual condition. Now to make that virtual condition, the tolerance has to vary as well. So in this case, our virtual condition is the feature minus the tolerance. So we have to make that the same throughout. So for the tolerance now we have 0.2, 0.3, 0.4, and 0.5. So this way, every single value, when we have the feature minus the tolerance, it always equals to our virtual condition. Now if we go to the next step, which is to do the resultant condition, which is going to be our outer boundary, the resultant is the variable feature size plus the variable feature tolerance. Now you can see in each case here that the feature size varies as well as the tolerance size varies. Now you might kind of wonder why the the tolerance changes. That, you know, in our GD&T we have a tolerance of 0.1, but now we show a tolerance of 0.5 here. How you have to think of this is that as the part gets bigger, it's able to have a larger tolerance to for the position to move around, while it still occupies the same amount of virtual condition. So I just have a quick little demonstration here, is that if you think of the shaded area there as the virtual condition, this is our first tolerance of, say, 0.1, and this would be our second tolerance with 0.2. As you have a circle with a larger size, you're able to have a larger tolerance for it to still stay within the virtual condition. So we're able to move this circle around to a greater degree than the smaller circle. And in all these conditions, all these cases, the both circles still remain within the virtual condition of the inner bounds. So as you get a larger circle, the tolerance gets larger too with this inner condition. And that's why with GD&T, rather than just giving a tolerance for where a certain component's going to be, you're giving it a tolerance with respect to the size of the part. So this allows you to include parts that would have been rejected. When they have a bigger size, they're able to still maintain the virtual condition that you want, and you give it a bigger tolerance and bigger area for it to stay within. So now we'll do the resultant sizes here, and the resultant size, like I said, was the feature plus the tolerance. So our first one is going to be 25.2, 25.4, 25.6, 25.8, and 26. So you can see with the resultant, we've created the outer bounds of 26, and the virtual condition is our inner bounds at 25. So with the GD&T and the dimensioning that we put on this part, we're able to complete this little chart that gives us our inner bounds and our outer bounds. And what this does is when we're doing our hard stacks or putting our components together, we're able to know the two conditions of our GD&T and how parts will have to fit in there. And that concludes our tutorial.